All right, thank you very much. It's quite an honor to be here. I think this is my third trip to UT Austin. The first one was when I was visiting as a potential graduate student. And I was trying to think last night, why did I not come here? And I don't remember. And then I came when I was at the end of my graduate studies looking for postdocs. And now I'm in this position kind of transitioning fellowships, but also maybe like thinking about permanent positions. So it's really nice to be back here at this like other transition in my life and see all of you here. I'm going to be talking about this funny title, Exoplanet Genetics, like what does that actually mean? And as I'll go into, I think host stars and their compositions have stories to tell or information to give us about the compositions of exoplanets, which is kind of the motivation for most of my talk. So first of all, starting with this premise that we have observed thousands of exoplanets now, and there are many more exoplanet candidates that haven't been yet confirmed, and they're pretty diverse. I could show this in many different parameter spaces, but the one that I've chosen here is a mass and radius diagram. So these are different mass-radius relations that have been proposed to try to fit all the different planets that we've observed with the goal of understanding why there's this variation in these parameters. In particular, I'm very interested in how this might translate into something like you see on the bottom, which is this weirdly flipped diagram, but the important part is these different colored curves which correspond to different bulk compositions of planets. And I could show a different diagram for more massive planets. Here's just the smaller ones, but the idea being, why are planets diverse? Why do we see ones that are very unlike those in our solar system? And actually, feeding back, what can that teach us about the planets in our solar system and how they might have formed and how we might be able to find habitable planets in the future? So I know we have a talk about biology tonight, so I hope I don't butcher this very badly. But I like to use this analogy about how do we learn about humans, right? This is from a real genetics journal, and there's these different components that all feed into how humans develop, how we grow and mature and live our lives. And so I will change this into how do we learn about exoplanets. And so there's their physiology, whether they have circulation or convection, how they're heated and cooled in their atmospheres or the interiors, their behavior, how they move within the disk, or scattered out of the protoplanetary disk, whether their atmospheres are evaporating, whether they have peer influence or peer stress from other planets or other stars. And then what I'll focus on sort of today is this host star aspect, what they're inheriting from their host stars and maybe the disk, and how all those things, like I said, feed into maybe life on planets. So I have a different version of this, which I feel like I have to update all the time and draw more lines in between. This is based on a review paper from 2014, but I've already had to add a lot in. And so this is focusing on this question of learning about exoplanet composition. And you can see that I have the stellar abundance part over there, but I just first quickly wanted to mention kind of the most basic way that we learn about them. The most kind of fundamental parameters, perhaps, are the planet mass and radius, which I showed on that first slide. And these are directly connected to the density and then the bulk composition of the planets. So while we really like to measure exoplanet density, and this is another a mass radius plot with these different colored curves which correspond to different compositions. And then these are known exoplanets with small errors in both the mass and radius. That's the goal, but it's really hard. Anyone who works on these types of measurements, I think, can appreciate. So here I'm showing the planetary radii. The color here is orbital period. And then the fractional uncertainty in the mass of the planet. And so even this population, this is where we have both the mass and radius measured, which is for the majority of planets, we don't have both of those measurements. But you can see as you get to the small, potentially interesting Earth-like planets, the uncertainty in the mass blows up. So that's not very good for understanding the density. And another way to look at this, to demonstrate how difficult it is now the color is still the orbital period. Now I have the x-axis as the mass, and the y-axis as the number of radial velocity or Doppler observations that were published with the mass measurement. The colored points or the filled points are transiting exoplanets, and then the open points are ones that were detected via RV. And so you can see immediately that for the transiting exoplanets, there are generally fewer observations needed. That's because we know when to observe to get the best radial velocity measurement. We're pretty confident there's a planet there versus trying to detect it. But again, as you get to these smaller masses, the number of observations that you need increases. And I've X'd out Alpha Cen B because we don't think that's actually a planet anymore, and put in Proxima Cen B, which is the square. This database is exoplanets.org. I believe it's maintained by a team of undergraduates, and so I've emailed them about this, but they haven't quite updated it yet. But this database makes nice figures. So anyway, density is hard. So how else can we learn about interior composition? Well, I'm drawing another little line between stellar abundances and interior composition, and that's what I'm going to tell you more about today, how they can inform interior composition models and inferences we can make. So first, I'm going to start out with just the host star metallicity, parameterized by the amount of iron in stars, not oxygen, which is, I guess, what galaxy people do, which is very weird to me. But just the iron, and the bracket means relative to solar. And so many of you may be familiar with the giant planet metallicity correlation. I'm showing a plot here. The red dashed line are giant planet hosts, kind of their relative frequency. And then the blue solid line is super Earth and Neptune hosts. And the dotted black line is stars without planets. And I have that in quotes because we think from Kepler that most stars probably do have planets. So these are stars or planets haven't been detected. You can see the red distribution is skewed over towards higher metallicities for these giant planet host stars. And then for the smaller planets, it's not as skewed. And so we think this is actually really good evidence of the core accretion formation scenario for planets, where you have this disk of gas and dust, and when it has a higher metal content, which is inferred from the higher metal content of the stars, or a higher surface density, you can form the giant planet cores faster or in enough time to then accrete gas onto the core and make a giant planet. And there's been lots of studies kind of helping to confirm this. One that recently came out is by some of my collaborators at UC Santa Cruz. This was led by graduate student Daniel Thorngren, when he used relatively simple but pretty robust models of the interiors of giant planets. These are cool planets, so they don't have this radius inflation issue. They have both masses and radii measured, and so he knows the density, and he can then use his models to try to infer the amount of heavy elements that are required to be in that planet to match the radius and density. And he finds this very nice relation between the planet mass and the amount of heavy elements or heavy element mass in the planets. And so this matches what core accretion predicts for the majority of systems. There have been many other studies trying to look at what the host star metallicity could tell you about planets. In this paper by Rebecca Dawson in 2013, they used the fact that the hosts of giant planets that are on eccentric or inclined orbits, those host stars seem to have higher metallicities than the host stars of giant planets that are on less inclined or less eccentric orbits. And they use this to suggest that planet-planet scattering was a more dominant mechanism for causing these orbits of the giant planets to not be well aligned, because the higher metallicity systems would form more planets and thus influence the orbits of these close-in giant planets. There have been a lot of papers trying to understand how this giant planet metallicity correlation changes as you go down to smaller planets. And I think the jury is still sort of out. A few papers have said there's no small planet metallicity correlation. There are a few papers that say there is, but it's just much, much weaker. I think that's still to be determined, but it certainly does weaken as you get to smaller planets. There have been these few works about focusing on the host star metallicity and the periods of the planets. And again, work by Rebecca Dawson, combining analytical estimates for the formation of planetary embryos with numerical simulations of gas accretion, basically showed that at longer orbital periods, these systems, starting with a protoplanetary disk and then forming planets, there aren't these longer period planets that are small around the more metal-rich stars. And she parameterized the metallicity with the surface density of the disk, and she suggested that this meant that embryos at these longer periods in more metal-rich systems are growing faster, and so they're able to accrete more gas, before the disk dissipates, and thus you don't see the smaller, sort of more rocky planets at the longer periods in the more metal-rich systems. And then also, Heiss Mulders last year had a paper out using data from the Lamoste survey of Kepler stars, showing that there's this increase in the metallicity of the host stars as you go to shorter orbital periods, such that it seems like short period planets prefer to be around more metal-rich stars. And there are a couple different ways to explain that that I'm not going to get into now. We're not quite sure exactly why that is, but that was something that I was interested in, as was a graduate student at the University of Virginia, whose name is Robbie Wilson. And so we set out to investigate this planet metallicity period issue using a sample of stars, Kepler stars, measured with apogee 2, which is what Rachel mentioned. This is a near-infrared spectroscopic survey in H-band, about 22,000 resolution. The first thing we had to do was validate the parameters that the automated parameter pipeline from Apogee produces. Apogee really is a red giant star survey. It's not, the majority of the sample is not dwarfs. But we convinced ourselves that the metallicities coming out of the pipeline are reliable for dwarf stars. And then we set out to compare that with different planet parameters. And the takeaway, what Robbie found, is that not only is there this increase as you go to shorter period planets, their host stars have a greater metallicity, but there's a critical period at which this difference occurs. And he did this by breaking the sample of about 300 Kepler objects of interest, single planet systems, at a bunch of different periods, and then testing whether the metallicity distribution in those two groups was very different or not. And so you see he finds this minimum in the p-value, comparing those two populations, around 8.5 days. And so that's a little bit different than the Mulders result, where he said, well, it's around 10 days, something like that. He didn't really pin it down, whereas I think based on a lot of statistical tests, we think this is a significant result, and requires something like 0.1 dex or better precision in the metallicities to detect. So while our sample is less than half the size of that in the Mulders paper, our data are better, and so we can get the same quality of result. And what's interesting about this, or one of the interesting things about this, is if we take those, now that population of short period, high metallicity host star planets, and the longer period, lower metallicity host star planets, and now break them up by their radii, there's this match, roughly, to these two different populations of planets that were detected by B.J. Fulton in the Kepler sample, where it appears that there is a smaller radius peak in the occurrence rates, and then sort of a valley, and then another peak in the occurrence rates. And so this was a paper by Jin and Morisani trying to explain that about and folding in the composition of the planets. And again, we're suggesting that maybe small planets not only are forming closer into or prefer to form around these more metal-rich stars, but are also predominantly rocky. And so that maybe this is some sort of clue as to what types of stars we should be looking at to find these small, close-in, rocky planets. So that should be hopefully on the archive soon. So that's iron and the metallicity of stars. But what about other elements? There are plenty of other elements besides just iron. And in fact, this is one of my favorite diagrams because I think it really helps motivate my interest, which is showing the abundances of this one type of primitive solar system material, Ci chondrites, versus the abundances in the solar photosphere. And you can see that for many of the elements, including kind of these refractory elements, iron and magnesium and silicon, we think those are making up the bulks of particularly small planets. There's a correlation. It's easy to see by eye. And so that kind of gives confidence to the idea of, well, maybe we can use the abundances in stars to estimate something about the planetary building blocks in other solar systems. And so digging into this a little bit further, there have been many, many papers that have tried to compare planet hosting stars to not planet hosting stars in a bunch of different element spaces. And so this is a paper coming out of UT Austin looking at silicon and finding that it seemed to be enhanced in planet hosting stars. It seems that like at low metallicities, where maybe there isn't enough iron to form planets, that perhaps other alpha elements come in and fill in the gap where iron was left. And that so planet-hosting stars at low metallicity appear to be more enhanced in alpha elements. Lithium, this has gone back and forth in literature whether planet-hosting stars have less lithium because of the planet being closer in and somehow increasing the mixing in the star to decrease the lithium further. This is one example. There are certainly examples where they say, no, it's not different in planet-hosting stars, but it's interesting that you could use lithium to do that. And then there was this study 2 years ago by one of my now collaborators, Cayman Unterborn, looking at solar twins, looking at thorium, which is the radioactive isotopes of thorium actually, along with potassium and one other element, uranium, help heat the interior of our planet. And so the idea was to look at how the relative amount of thorium to silicon varies across both systems with planets, the filled symbols, and those without, and what that might mean for interior or internal heating of planets. And he found this great variation. And so that might mean that even, say, if the radius and mass of a planet is the same, if its interior composition is different, then that's going to create a very different internal composition, and composition for life. So I have done some work on the carbon to oxygen ratio, which when I was in grad school, this was like a really interesting thing for people. They were very fascinated with carbon-rich planets, both the small planets and then giant planets, especially their atmospheres, whether there could be high C to O atmospheres in particularly hot Jupiters. And so I looked at this sample of hot Jupiters, which are plotted in red here, versus other studies of stars, and basically found that we don't see a lot of carbon-rich planet-hosting stars. And so that might mean if you think, well, the disk material is related in composition to the star material, so the disk material maybe isn't carbon-rich, so how does that then make a carbon-rich planet if you can't have that? John Brewer looks at a much larger sample of mostly not planet-hosting stars, but stars being monitored for planets with radio velocity, and also found that there's just really a sharp drop-off in the C to O ratio, so that there's not these carbon-rich planets. What this means for giant planet atmospheres, I'm not sure yet. There, again, have now been some papers that have shown, based on formation modeling, that it doesn't really matter the composition of the disk or where in the disk you form it, that their giant planet atmospheres don't seem to be carbon-rich. So that's, I think, still maybe an open question. But certainly for the small planets, it's softened the excitement for like diamond carbon-rich planets. If you had a very carbon-rich planet above a C to O of about 0.8, that's going to change how silicon is distributed, could make a very different type of planet than what we see in our solar system. But again, that doesn't seem to be the case, and it's backed up by these studies of polluted white dwarf atmospheres, which also show that there's not this enrichment of carbon in kind of the leftovers of small planets. So I'm going to focus in now on a few questions that I've been working on, all related to the interiors of planets. So the first is, what are giant planet interiors made of? And how can we use host star abundances to inform these questions? So I'm coming back to this paper by Daniel Thorngren from earlier this year, where again, he showed that based on these interior models of a core and then an envelope that is enriched in heavy elements, that the planet mass is related to the heavy element mass, but doesn't seem to be super dependent on the host star metallicity. And so this is an extension of a paper that Miller and Fortney wrote in 2011. They find actually a weaker correlation than the 2011 paper. So that's kind of disappointing. But looking at a different relationship, so now not just the heavy element mass, but the enrichment of the planet, so kind of heavy element mass over total mass. This ZP has some relationship to the total planet mass, but it seems to be stronger when you include or when you normalize by the metallicity of the star, the Z star. And so we're very interested in whether or how the star's metallicity factors into how much heavy elements end up in giant planets in their interiors. So we're looking at other elements besides just iron, because there's no really reason to assume that giant planet interiors would have a lot of iron. If they're forming kind of far out on the disk, maybe they would be dominated by water ice or carbon ice of some kind. So we can make similar plots as the one that I just showed down here, ZP over Z star, but instead of calculating it based on iron in the star, we can calculate it based on different elements, which I've shown here at the top. You can just ignore the numbers for now. But you can see in all these plots, there does seem to be some relations, but there's also a lot of scatter. And so the errors on the Y error bars on these points are really mostly dominated by the errors in the planet parameters, so the masses and radii, which then enable us to calculate the ZP. So that's kind of disappointing. We can try to get more data, which is what we're trying to do now, and or we can look at it in a different way. And so Daniel did this great principal component analysis, which I hadn't done for a few years, which he takes these parameters, so the total mass of the planet, the mass of the metals, and then these stellar abundances that we're measuring, and breaks it down into the principal components, so basically the planes of most variation in that multidimensional space. And so the top of each of these columns are the eigenvalues that correspond to each of these eigenvectors. And from left to right, it's the ones that represent most of the variation moving from left to right. And so the first column kind of makes sense. All of the stellar abundances are contributing a lot to the variation in that eigenvector. The second column, all right, you can see that the mass of the planet and the heavy element mass are related. We already knew that. Oh, you can sort of, hard to see. Anyway, you can tell by the colors. But in the third column, this is particularly interesting because it's showing that there is some correlation between the total mass of the planet, the metal mass in the planet, and the carbon and oxygen abundances in the star. And so maybe this actually means that the interior compositions of planets really are associated with the relative enrichments of carbon and oxygen in the disk, and that we can tell something about that just by studying the current composition of the star. So this is definitely work in progress. I'm trying to analyze data now, but this was really interesting to me, and really something that's only possible to do with this much larger sample of giant planets than what we have in our solar system alone. So that was giant planets. But really what I'm interested in personally is the small planet interiors. And so looking at this, there was this super exciting result that came out when I was in graduate school that I think spurred me to get interested in stellar abundances as a tool to study exoplanets, which was a study by Jorge Melendez, in which he looked at a sample of 11 stars that were very similar to the sun in their effective temperature and surface gravity, and did a differential analysis between each star and the sun, and found that the sun, relative to these solar twins, seems to be depleted in these refractory elements with higher condensation temperatures. And he suggested that this is potentially a signature of small planet formation in our solar system, that this material that the sun is missing, this heavy element material, went into the small planets in our solar system. And my colleague at Carnegie, John Chambers, had a paper in 2010 where he did sort of a back of the envelope calculation and tried adding back into the sun different compositions and different amounts of material to see if he could reproduce this solid line trend that was found by Jorge Melendez. And he found that adding in 4 Earth masses of a mixture of Earth-like material and another type of primitive solar system material, CM chondrite, kind of matches the trend. He doesn't have error bars. It's, like I said, sort of back of the envelope. So this was kind of exciting. But subsequently, a lot of papers have come out showing that this type of trend depends a lot on the ages of the stars, where they formed and where they are now in the galaxy, whether they were affected by nearby supernovae, how dust and gas is separated in the disk, and what goes into planets and what doesn't. So it's a much more complicated story. It's not so cut and dry. And so you might think, well, this is a great technique, doing this differential analysis, trying to find 2 stars that are very similar to each other and just checking their relative abundances. But how do we get rid of all these other factors that might complicate that analysis? And I just also wanted to mention, I've done work with Simon Schuller looking at stars that we know host small planets. And so if we know that they have small planets, we would expect them to have this same depletion in the refractory elements, and we don't see that. And so you would expect the lines to slope down, and in almost every case, they're either straight or going up. But thankfully, we do have samples of stars that are exactly the same, that formed at, we think, the same time, in the same place, were affected by the same environmental conditions. And these are these twin binary stars. And so if these types of stars don't have the same composition, could that be a signature of planet formation, the same type of signature that Jorge was looking for? Material could be missing from one star, either being in giant planet cores or small planets, or maybe it was a planet that was ejected from the system, or could be added to the star, maybe giant planets migrating inward, pollute stellar atmospheres, or like this planet-planet scattering idea could fling material onto the star. So I've written several papers about this. There have been other papers, which I'll show in a moment. I just wanted to walk you through one example of this, which was kind of special because I also discovered the planets, so that was kind of cool. This was a binary system detection, twin stars, and one of the stars has 2 planets, and the other star has 1 planet, and they're all sort of on the giant planet side. And I could do this differential analysis. So in the top plot, I'm showing the A star minus the solar composition, which I measured as reflected light from the asteroid Vesta. And you can see that, yes, the stars do appear to have the same abundances for most elements, and that they're both very, in the planet world, pretty metal poor, having a metallicity of something like minus 0.3, which is interesting because we saw before that giant planets tend to be around more metal-rich stars, and so actually the probability of finding giant planets around this type of star is quite low. So to find them and then for it also to be a binary was like gold mine. And then in the bottom plot, I'm showing now just the total, the differential abundances between A versus B in orange and then B versus A as the blue stars. And now you can see that for the more volatile or lower condensation temperature elements, there's not as much of a difference, but that difference increases as you go to the more refractory elements for something like a mean difference of like minus or plus 0.03, which is not very big. And so that's like a typical error on abundance measurements, if not higher. This is really only possible by doing this strictly differential analysis, just comparing one star to the other versus one star, say, to the sun, which might have a slightly different temperature or composition. So just quickly, why might these stars have different compositions? How could this be related to planet formation? I can do a very kind of hand-wavy calculation looking at the difference in the masses of the minimum masses of the planets that I detected around both stars and trying to add that mass difference back into, in this case, the A star, because it has if you look at B minus A in blue, A is depleted in these elements and has the lower mass planets. So if I try to do that, a late timing addition of that material gives a metallicity difference that seems too high based on what I'm actually observing. And an earlier time, where the convection zone size of the star is larger, gives a metallicity difference that seems to maybe make sense. But this is making a simple assumption about the composition of the material that I'm adding into the star using just a ZP of 0.1. But if instead I estimate the heavy element mass based on the masses of the planets that I know and the relation from the Thorngren et al. Paper, I still get that a late timing accretion gives a metallicity difference that's a little bit too high, but then an earlier timing gives ones that is a little bit too low, but maybe somewhere in between there. The point of all this is not that it definitely happened at this time, but that you can use these stellar abundance measurements to start to place constraints on, for instance, the timing of this accretion onto the star's photosphere. There have been, but it's also, there could be lots of uncertainties, like whether there are other planets, whether material was ejected from the system. There's uncertainties in the giant planet interior models. So, like I said, still kind of hand-wavy at this point. These are some of the other papers that have looked at twin binary stars. This may look like a lot, but really we're talking about like less than 10 systems where this has been done, just because finding planets around these twin stars, the twin stars don't occur that frequently, and then finding planets around them is hard in itself. So I think right now we're still in like the butterfly collecting stage, but this is a field that I'm really excited about because I think it's, even with a small number of systems, we can make progress in understanding how solar compositions might be affected by planet formation. Okay, but that really wasn't about small planets. I was talking about giant planets. So really, what about the small planets? So I showed you before that plot of the solar composition versus primitive material, and there was that pretty tight correlation between their two compositions. There's also been papers that have looked at trying to model the interior compositions of planets, either taking information from the star as a prior or not. And so one of my favorites is by Caroline Dorn a couple of years ago, where she, in this case, is just testing this type of modeling on the Earth. And so case A, and it's sort of hard to tell with this color scheme, but the red is the prior that she's using. The green is the known measurement, like this is Earth. We know what, for instance, the mantle weight percent is in silicon, and the mantle magnesium silicon ratio, at least much better than we do on other planets. And then the blue is the posterior distribution. And in case A, she's not using any information from the sun, its composition, in her modeling. And in case B, she is. And you can see that the match between the posterior and the actual independently inferred results is better when she's using the solar composition information. And so she did this on a few other planets, and I think, again, it's still sort of in the initial stages, but this is very promising, showing that if you can measure the compositions of stars and use that in your modeling of the interior compositions of small planets, you can perhaps get better constraints on their compositions and things like core radius. So this is kind of part of a larger program question that I'm interested in, which is using stellar chemistry to sort of search for clues as to the rarity of the Earth-likeness of planets. And so we think for life to exist on a planet, we need some sort of sustained surface liquid water, maybe not surface, but sustained liquid water. But to have that, you need the right atmosphere. And the atmosphere that you have on the planet is related to the interior composition through the surface temperature, and then also the atmosphere affects whether there's going to be weathering in the rocks. The interior of the planet spouts out different volatiles, and so that then affects your atmosphere. The interior composition also influences how quickly the core will cool, and thus whether you're able to develop a magnetic field around your planet, which then also helps retain the atmosphere. So it's kind of this whole planet coupling idea where all these different components are going to be important to understand for understanding how Earth-like a planet is. And so I'm starting to tackle this question with several people, including Cayman Unterboard, who I mentioned. And so a few papers that we have out or are working on. One is looking at basically how likely it is for a planet to have plate tectonics by seeing whether it would have a composition of plates that would float or sink. So on the right plot, we're looking at this as a function of the bulk planet composition, the magnesium and silicon and iron abundances. And then this FC parameter is based on the buoyancy force, or it's a parameterization of the buoyancy force. And the black points are calculated directly from MELT's models of planets. Those compositions are within this modeling database. But then we can use that data to fit a relationship between, in this case, the sodium to silicon abundance, and then extrapolate that out to the red points and the open squares, which aren't in this database. And so you can see that there's kind of this, again, wide variation in the stars, even just the red points focusing on those. Those are known stars that host planets from Kepler. A wide variation in whether they would have plates that sink or float. And so that's interesting. In the same paper, we have this nice ternary diagram, which I always have to remind myself how to read. But if you follow just the solid lines, you can see that, again, focusing on the red points, the interior compositions of these planets can vary widely, and that can affect the core size of the planet and thus the density. And we can use, interestingly, the composition of the star and these types of interior models to try to predict, for instance, for these Kepler planets, what their density will be. And I think that's really, I'm excited about trying to test that out with the mission that I'll talk about in a moment, because right now, a lot of these assumptions are based on what we know about the Earth. And right now, that's the best we can do. We don't actually, my understanding is, know the composition of Venus that well to really use it to constrain these types of models. But going out and measuring solar stellar compositions, as well as either the masses or radii of planets, and then getting the other parameters and testing the models. We'll be able to do that soon with a mission that I will mention in a moment. So far, all of these studies of elements beyond iron in small planet host stars have been comprised of pretty small samples. The one that I just showed with the Kepler stars, that was something like 100 stars, 100 systems, but really we want more. And so there's a mission launching, hopefully in March, called the TESS mission, which you've heard referenced before. And what will be great about the TESS mission is it will find, or is predicted to find, these orange points of planets. And so planets that are much closer, their stars are brighter, they're easier to follow up, both for determining the masses of the planets and the stellar compositions. You can see the Kepler field right there. So I'm very excited about this. We know, based on the occurrence rates of planets, that small planets seem to form around small stars, particularly M dwarfs. And that's also an easier place to probe the habitable zone because it's closer in. And so I think a real boon for the test sample will be using this apogee instrument, which operates in the near infrared, to be measuring the compositions of stars, and particularly M dwarfs. And so this is another really exciting paper that has come out of apogee, looking at analyzing spectra of M dwarfs and determining abundances like calcium and aluminum and silicon and magnesium, things that we never have measured in M dwarf atmospheres before. And so this opens up a huge parameter space, new parameter space to work in for these small planets compositions in particular, like Proximus NB, the TRAPPIST-1 planets, and LHS 1140. And these are just some recent detections of these small planets around cool stars. And so this is a program that we started with Apogee 2 South, which Carnegie has access to. This is a clone of the Apogee North instrument. And so I think Rachel briefly touched on this. We've started this pilot program to observe the TESS Southern Continuous Viewing Zone with Apogee, looking at H-band 7 to 11 targets. I think we haven't gotten any data yet, but it looks very promising so far. We just put in another proposal for 2018B. And this is part of a pre-survey for what was after Sloan 4, AS4, until yesterday, when we heard that Sloan approved our proposal, and so it is now officially Sloan 5, which will be this all-sky survey, spectroscopic survey, multi-epic, both in the near-infrared and optical. The test stuff will be focused on the near-infrared, which will be super exciting, getting stellar parameters, stellar abundances for all these stars, many of which we'll find planets. So, takeaways. I hope that I've given you a little bit of a taste of how host stars abundances can be compared to different planet properties to constrain when and where and from what the planet material formed. I think we're still sort of in the shadows with regard to both giant planet interior compositions and small planet interior compositions, but that stellar abundances provide a way to make more meaningful constraints and at least make the parameter space that we're searching in a little bit smaller. And then, like I said, TESS has this potential to significantly expand our knowledge of small planets and the number that are close to us and around stars that we can easily follow up and then learn about their formation and composition. So with that, I will take questions.
Questions? Yeah, thanks. One quick comment, one quick question. Mm-hmm. My understanding from the specifics and the generals is that the things you're looking for basically come out when you do differential. Therefore, you provided that list of other people who've done exoplanets or planet host metallicities. You know what the advice is. Go back and do every one of those stars yourself so that you can control the system. And the question is, when you're taking everything from F stars to N stars, in your work, when you are trying to control the uncertainties, what are the excursions in stellar parameters at which you say, you know that? Really thinking about getting to the limit of what I can do?
Yeah, that's a great question. So in the work that I've done so far, I was a little bit involved with the M-Dwarf work, but not so much. So I think most of my stuff has been FGK. And so in terms of like effective temperature, once you get to the hotter stars, as you know, they tend to be harder to do. And so I usually stick to like less than 6,500 Kelvin. And then in terms of the cool stars is really where I've been hitting the wall, because a lot of these planet host stars are cool. And so I have several in these samples that I'm studying that are like 4,200 Kelvin, and it's just lines. And so I think somewhere around the 4,500, 5,000 Kelvin mark is where the type of work, differential work that I've been doing certainly becomes challenging. But again, perhaps moving into the infrared, even for not just M-dwarfs but also K-dwarfs, is the way to go.
Other questions? I will get into my chair prerogative. So the question about the binaries.
Yeah.
So you mentioned that the sample's pretty small. It seems like you could do a targeted RV or transit source that specifically just goes after wide binary. Is that something that's going on that you're planning?
So that's not something that I've planned. There are a few that just happen to fall within the long-term RV survey that I'm part of, and that one that I showed was an example of that. I think that I talked to John Brewer at the Know Thy Star, Know Thy Planet meeting, and he said that there are a few in the sample that he's been working with, which is the high-res sample, that are these twins that they seem to see a large difference in the abundances, and then they're going to go after them and target. There's also been a survey looking at known solar twin stars for planets, and that's been led in part by Jorge, but also Megan Bedell and Jacob Bean. So things sort of like that, but I don't think I've seen a large targeted survey of known twin stars for planets. That would be great.
Okay.
I apologize if you said something along these lines and I missed it, but I'm curious if there's some metallicity threshold for planet formation. And that's just kind of a general question, but I know this is outside any hope of observing, but if you get down to low enough metallicities in a galaxy, like, for example, the dwarf galaxy, would there be any planet formation possible? And I don't know if you have any constraints or interest in that.
Yeah, I absolutely do. So this is a question that I've been thinking about a little bit recently. So I think the lowest metallicity system in terms of the host star that's been detected, that has planets detected, is something like -1 Fe over H. But there are certainly systems where there's lower metallicity, and we could potentially look for planets, especially with the transiting technique. And so I actually have, I think like right now, K2 is observing some stars that I asked them to observe, and that they said okay, that have very low metallicity, something like -1.5. This is actually a twin system. I was lucky enough to find it in the K2 field. And based on the abundances of the stars and their velocities, people have suggested that they actually didn't form in our galaxy, that they formed and were accreted. And so if I found planets around those stars, that would potentially be the lowest metallicity system where planets were detected. But I think what is the low threshold? I think that's still an open question. Yes?
Yeah, along those lines, I've been very interested in exactly that, but
Yes.
very low metallicity planet host stars. And you're right, the lowest ones are around -0.8, -1.
Yeah.
But the very interesting point is that at that metallicity, the planet host stars are disproportionately thick to stars with enhanced alpha elements.
Yes.
So I think that by itself is telling us a lot about the process of star formation, planet formation, and which elements are important. Because you look at the alpha elements, well, rocks are the
Yes.
sides of the alpha.
Exactly. Exactly. Yes.
And then the planet is made of that, and
Yep. Yeah, great comment. And I showed, right, that plot that for those, the alpha enhanced planet host stars, those were all giant planets that had been in that survey, and it wasn't really going to super low metallicities. But I think you're absolutely right. Like these alpha elements, what's going on there? That's very interesting.
It also means that planet formation got started very early.
Yes.
in the galaxy.
Yes.
All right, it's a lot of good questions, but I think we'll have to cut it
Okay.
there. Let's